So what is self-organized maps? It is a methodology to organize information in the subsurface, the way we're using it. And so you have a file cabinet, and in that file cabinet you have folders. And maybe your folders, one folder has all your electric bills, and one folder has all your car payments, and one folder has all your apartment payments. So you're organizing your information in ways that have similar information pieces to a folder. Well, that's what self-organized maps do. And the work that we've done and what SOM is based off is some of the studies that were done by Dr. 𝗍𝗶𝗿𝗁, who wrote basically the mathematical algorithm for how we're using to organize data. And he published a paper in 2001 where he had gone to the UN and he had asked for statistical information on 117 different countries. And they gave him 39 different pieces of information for each of these 117 countries. And he wanted to see if he could find a way to organize all that so that you could see each country, country by country, and the information that went along with it. And this is a list of the countries, and the way we're using with seismic data is the 39 statistical pieces would be equivalent to different attributes in the seismic. Okay, and when you come out with that, you have organized all the information into a map, in this case, a map of the world, and you have all these different clusters of information that are pertinent to each country in the map. So what we have done is we are using different seismic attributes to help us create a map of clusters of different rock properties. So each of the countries up there, and you can see Canada and US are the same color, and they light up as the same color on the map. So each of these clusters have the same basic rock property information in them. Software that's out there right now are using wavelet-based information. We have decided that we get better statistical information if we reduce it down to sample. So in this particular example, if you have a wavelet from trough to peak, that's 30 milliseconds, and you have 2 millisecond sample rate, we are parsing that data and statistically analyzing it 15 times as densely as you would if you were looking at a peak or a trough, which is why we get the detail in the subsurface that Robin's able to utilize with his modeling. And we're looking at multiple seismic attributes at one time because each attribute has its own particular kind of information that it carries in the subsurface. So as you can see from all these different wavelets for each of these different attributes, they're carrying a little bit tiny bit different piece of information. All this information on every line, on every trace, at every sample goes up into a data cloud where it's normalized and organized and then comes back down to earth as what we're calling lithology. So we see all these little pixels right here, and I've got a kind of a wavelet overlay on that. So we're looking at the subsurface in much greater detail and can see much better resolution than you can in the wavelet world. In fact, a lot of people refer to tuning thickness in the wavelet world. We look at resolution. And so if we know the bin size, we have the sample, and we know the interval velocity of the rock, then we can pretty much say that, okay, if I'm looking at a carbonate in the subsurface, regardless of depth, because I'm looking at sample statistics, I can see something that's 5 to 8 feet thick. And if we're looking at clastics based on their interval velocity, I have had a discovery where I was looking for a 4-foot thick sand at 11,000 feet deep. And when you can start getting into the subsurface and you can find thin beds, then you can start really understanding the depositional models.